Alright, so this begins prequel 2 on modular arithmetic. So we aim to explain what Zn is in this section, how to construct it, how to work with it, and why it makes sense. And also a little bit about why it's useful. So here's the definition. A is congruent to B mod n if and only if n divides B minus A. Alright, so that's the definition of congruence. That means that the difference of A and B is a multiple of n. Alright, so this is even nicer if we look at theorem 1.2.3, which says that A and B are congruent mod n if and only if A and B have the same remainder when divided by n. Alright, now I was just getting very confused reading my own proof, which is never a good sign, when I realized I have done something unfortunate, which is instead of putting what I meant to put here is suppose A and B are congruent mod n and A and B, actually not even that, this is still wrong, I'm sorry, just forget about this right here, cross that out. Alright, cross that out, and we're just going to say suppose A and B share the same remainder after division by n. This is what's meant here. Sorry about that. Anyway, with that fix, by the division algorithm, there exist quotients q1 and q2 such that A is equal to q1n plus r, and B is equal to q2n plus r, right? Because they have the same remainder after division by n. And then if you take their difference, what you get, since the r terms cancel, right? And you're just left with the difference of the quotients times n, which shows you that n divides b minus a. Alright, well that wasn't too bad. What? Alright, so then the other direction for the proof, so I'll have to edit these notes and send you an updated version here, but conversely, suppose n divides b minus a, then that means that b minus a is a multiple of n, and you can apply the division algorithm to find quotients q1 and q2 and remainders r1 and r2 for dividing a and b by the dividing number n, and like so and so, right? And again, remainder 1 and remainder 2 are between 0 and n, not including n, of course. And notice that the difference between r1 and r2 has to be less than n. We saw that idea in a previous proof. Anyway, then b minus a is equal to the difference of q1n plus r2 and q2n plus r2 and q1n plus r1, which gives us this. Therefore, if we solve for the difference of the remainders, that gives us that q minus q1 plus q minus q2 rather plus q1 times n is equal to that. Of course, n is positive, so I pull it out of that absolute value. But we also know that that the absolute value of this piece right here, q minus q2 plus q1, well, that's non-negative, and so that means that we also know that r2 minus r1 is less than n, so it follows that this must be equal to 0 because otherwise there's no earthly, I mean, you just think about it, this cannot be less than n, and this be a multiple of n that's 1 or larger. That would violate this inequality, right? So it forces the absolute value of the q's piece to be 0, and once you know that's 0, that forces the difference of the remainders to be 0, which then forces us to have r1 is equal to r2, which is what we set out to prove, right? Which is that if a and b is congruent mod n, then that implies they have the same remainder when divided by n. Okay, so now that we have that out of the way, let's go on. Congruence is a equivalence relation, right? In particular, x is congruent for any positive set of positive integers, triple positive integers, x, y, z. X is congruent to x mod n. If x is congruent to y, then y is congruent to x. And we also have transitivity, right? X congruent to y and y congruent to z implies x congruent to z mod n. And the proof of these things is pretty straightforward. You can either think about it in terms of remainders, or you can think about it in terms of multiples. I actually prefer to think about it in terms of divisors and multiples personally. Anyway, here's the argument for reflexivity, because x minus x is 0, and 0 is 0 times n, which shows you that the difference of x and x is divided by n, which goes to show you that, of course, x is congruent to x. The argument for symmetry is similar, and transitivity is also similar. I will let you look at those. All right. And you might notice that to prove 3, we end up having n divides y minus x and n divides z minus y, which means that n divides the sum of these two things, right? But the sum of these two things, the y's cancel out, and it just leaves you z minus x, which goes to show you that n divides z minus x, which is to say that x is congruent to z mod n. So here we're actually referencing prequel 1, where we learned that if we have like a divides b and a divides c, then a divides a plus c, etc. All right, moving on. So corollary, congruence modulo n forms a relation, an equivalence relation on z, rather. So that immediately informs us that there's an interesting partition of the integers which respects this equivalence relation. You should recall that a partition of a set is a family of subsets such that these subsets are disjoint, and their union covers the whole set. Now, I'm missing an important word there that I keep forgetting to edit, but family of, there's an important word right here. The important word that's missing is non-empty. All right. Now, some people would say that this equivalence relation affords that partition or something. I think that was the language, but anyway, that's the partition. So what is the partition corresponding to the equivalence relation? Well, let's get into that. We define. So here it is. Equivalence class of the integers modulo n, and my first notation for that is just x with brackets, like so. All right. So what is the equivalence class of x with respect to the equivalence relation z mod n? Well, it's the set of all integers y such that y is congruent to x mod n. We will also use the notation x sub n to emphasize that it's the equivalence relation with respect to n. All right. So there are several ways you could look at that. Right. So of course, just what I wrote, the definition, but x congruent to y congruent to x mod n is to say that y minus x is equal to nk for some k and z, which means we could rewrite the set as the equivalence class of x is actually x plus nk, where k is in z. I personally prefer to think of the equivalence class of x in this way. That's just me, but there it is. That's a sort of parametric viewpoint in some sense. All right. Well, so in other words, the equivalence class of x is x plus all multiples of all integer multiples of n. All right. So the equivalence class of x is a set of integers, an infinite set. So here's an example. Of course, these things are useful. Congruence mod 2 partitions z into even and odd integers, right? So you notice we have the equivalence class of 0 is 0 plus 2k, which is just 2k, and the equivalence class of 1 is, well, I wrote x plus nk, now I'm writing nk plus x. That doesn't matter, of course, because integers commute under addition. And this, of course, is going to suggest the coset notation we'll get to in a second. But anyway, congruence mod 2 partitions the integers into even and odd. If we looked at congruence mod 4, we'd partition the integers into these four classes, things of the form 4k, 4k plus 1, 4k plus 2, 4k plus 3, right? And if you work the right problem in calculus too, you can kind of stumble upon these things. But now this coset notation is real nice. I'll use it up here. You see this is 4z. This is 1 plus 4z. Or some people could write 4z plus 1. I mean, we got choices. You can write it one or the other. I think I stick with like 2 plus 4z for now, though. This would be 3 plus 4z. So this is the so-called coset notation. That was supposed to be coset notation. All right. Of course, coset is a technical term which we will give technical meaning to in due time. But for now, we'll just use the word like it's like a label, like you might name a child. You know. So my child, coset. Right? Oh, coset's so cute. Why not? All right. Anyway. Okay. So again, here's the coset notation. NZ is just multiples of integer multiples of n, and then a plus nz is exactly. I mean, this is precisely just to beat a somewhat dead horse. Here it is, right? I don't know why anyone would beat a dead horse. That's kind of odd. But maybe I'm just from the wrong time period to appreciate the expression. But the equivalence class of A, or the residue of A, is A plus NZ. All right. These are also called the residue class, mod n, I think. So there you go, even and odd, and here's the 4z. Let's get on with it. We should pause to note a subtle aspect of the notation. It is crucial to note that equivalence class of x equal to equivalence class of y does not imply x equals to y. For example, modulo 2, the equivalence class shared by 1, 3, and 7, and I don't know the name for that number. Those are all equal, but of course the numbers inside the brackets are not equal. Likewise, the equivalence class of 2 minus 42 is all the same, right? But it is not. You cannot say that 2 is equal to minus 2, and you cannot say that minus 2 is equal to minus 42, not as integers anyway, right? Or down here, modulo 9, we have 1, the congruence class of 1 is equal to 10, congruence class of 10 is equal to the congruence class of minus 8, and so forth, right? All right, so, and you notice that the congruence class of 1 and 3 are not the same modulo 9, and yet, right, so, this is where I introduce the, so the coset notation makes it clear, right? Like 1 plus 2z is equal to 3 plus 2z, but 1 plus 9z is not equal to 3 plus 9z. This is the, or better yet, there shouldn't be any danger for confusion, because what we have is we have that 1 with respect to mod 2 is equal to 3 with respect to mod 2, but of course 1 with respect to mod 9 is not equal to 3 with respect to mod 9, because 1 and 3 are different equivalence classes with respect to mod 9. Why are 1 and 3 the same equivalence class? Because 3 minus 1 is a multiple of 2. Is 3 minus 1 a multiple of 9? No, 2 is not a multiple of 9. That's why these are not equal. All right? So anyway, proposition, and I think this is actually entirely redundant at this point, but here it is. We have that the congruence class of x is equal to the congruence class of y if and only if x is congruent to y mod n. In other words, the coset x plus nz is equal to y plus nz if and only if the difference of the representatives y minus x is an element of nz, which is to say that y minus x is a multiple of nz. All right, so the proof is just rehashing the notation we've been talking about. Might be profitable. Let me read through it here, see if we think it matters. It's probably a good experience anyway to work with these things, just to appreciate some of the nuances here, even though I think logically this has already been proved. First of all, x is an element of the equivalence class containing x, right? Can you prove that? Hope you can prove that. Because x plus n times 0 is x, right? So it's in there. x is congruent to y, then that means that x is an element of y because these sets are equal, right? What that means then is that there exists a k such that x is equal to y plus nk. Consequently, x minus y is equal to nk, and we find that x is congruent to y mod n. Conversely, if x is congruent to y mod n, that means that there exists a k such that the difference of y and x is a multiple of n by k, and so x is equal to y minus nk, and y is equal to x plus nk. All right, great. Suppose a is an x, then that means in the equivalence class containing x, that means that there exists a j such that a is equal to nj plus x. And so we can solve that. But what I do, I replaced x, right? I replaced this x with y minus nk, right? And so then regrouping things, I've got n times j minus k plus y, which is in the equivalence class containing y. So what I just did was I took an arbitrary element of the set with the equivalence class with representative x, and I showed that that arbitrary element a was also a element of the equivalence class with representative y. That implies that x is a subset of y. The residue class the equivalence class represented by x is a subset of the equivalence class represented. I'm getting very tired of saying equivalence class. But anyway, that is a subset of that, because I just picked an arbitrary element in here and I showed it was also an element of the alleged superset. And you can make the same argument in the opposite direction, and to get that y is a subset of x, the equivalence class represented by x, which then of course shows that the equivalence classes are equal, which is what we wanted to do. So I think this proof, maybe this proof is necessary if you haven't started, if you took my, if you took this as the definition of equivalence class, then perhaps this proposition is necessary. And that's probably why it's here, because I think left to my own devices, I'd make that the definition. All right, anyway, so let's go on. So proposition. Now this proposition is super important. Really, really important, because this is the basis for working with Zn, as we usually do. All right? So if we have the equivalence class represented by x is equal to the equivalence class represented by x prime, and if we have the equivalence class, if we have representative y and representative y prime for a particular, equivalence class mod n, right? In other words, if we have two different representatives for the same, for this class and two different representatives for that class, all right, then it turns out that the equivalence class generated by the sum of the representatives is the same whether or not you pick the unprimed or the primed. And likewise, the product doesn't care about your choice of representative, and the difference doesn't care about your choice of representative like this, right? So that's very helpful, because that means that I can then define addition, multiplication, even subtraction on equivalence classes by simply adding or multiplying the representatives. All right. First, let's prove this proposition. Here it is. Suppose that we have this and that. That means that there exists j and k such that x prime is nj plus x and y prime is nk plus y. And I use the plus minus notation because, I don't know, I should just get rid of, no one cares about subtraction. I just get rid of 3 and just prove 1 and 2, that'd be enough. Anyway, fine. X prime plus or minus y prime is nj plus x plus or minus nk plus y, but then you can rearrange the n terms and the x plus or minus y like so, and that shows you that x plus or minus y prime, x prime plus or minus y prime is congruent to x plus or minus y, right? Which is to say that these two equivalence classes are the same thing, because their representatives are congruent. All right? And the proof, so I proved 1 and 3 at the same time, just to be confusing. Proof of 2, very similar. X prime y prime is nj plus x times nk plus y. Regroup this, keep all the n stuff together. N times this integer, ugly as it may be, it's an integer, and you got xy. So this shows you that x prime y prime minus xy is a multiple of n, which is to say that x prime y prime is congruent to xy. All right? So that gives us that that's equal to that. All right, so that motivates the definition, which I'm about to make, I think. What's this corollary? All right, if you want to think about what I just wrote in terms of congruence, there it is. That's kind of important to know, because then if you want to manipulate congruences like you manipulate equations, this kind of gives us license to do that, doesn't it? Right? So this, in some sense, says we can add congruences, mod n, right? And so I could multiply congruences mod n with this. Take the difference of congruences mod n, like that. All right. Oh, and that's my next example, is doing exactly that. I, for some reason, have an extra s in subtract. Anyway, so I'm solving this congruence, 2x congruent to 4 and 2y congruent to 2 mod 4, and to do that, I actually just look at the 4 cases there are to consider. Let's see here, what do I do? X, oh, actually I'm solving that. I added these congruences to get the y's to cancel, and then I subtracted them to get the x's to cancel and to get this, right? So since we're working modulo 4, there's just these 4 cases to consider, either x's in the 0, in the 1, in the 2, or in the 3. And I just look at the cases I look at the 2x congruent to 4 case by case, I think, here. So if x is 0, 1 doesn't work, 2, so 0 and 2 work for x, right? And I think this is a little bit misleading, because I really am also thinking about, over here, I'm thinking about y being one of these 4 cases as well, right? These are y, these are not x, because I'm looking at that equation. So, so there you go. 2 times 0 is 0, but it's not congruent to 2. 2 times 1 is 2, yay. 2 times 2 is 4, which is not 2, modulo 4, right? 2 times 3 is 6, but 6 is congruent to 2 mod 4. So we either have y equals to 1, y could be 1 or 3 in terms of the representative. And so x in here and y in there form a solution set for this system of congruences. All right, well, that was not that much fun, in my opinion, and it would just get worse if we had a higher modulus, right? So maybe we need a better way to solve systems of congruences, but that's not what I'm going to talk about today. Anyway, in fact, actually, well, to be fair, what I'm about to talk about would actually give you kind of a better way to solve a system of congruences, but maybe not that one. All right, I'm going to shut up about that. Solving systems of equations over Zn is a kind of tough thing, all right? I'll just say that for now. But before we try to solve systems of equations, or system of congruences, rather, maybe we should first understand a little bit more about what is congruence and what is this Zn thing I'm talking about. So here it is. I should remind you that a binary operation is what? It's a binary operation on set S is simply a function from the Cartesian product of S with S to S itself, right? In other words, it's a single-valued assignment of pairs in here to an element of S. So we can define a binary operation on the equivalence classes by the following rules. We can say that equivalence class X plus equivalence class Y is the equivalence class of X plus Y, where this is integer addition, and likewise the product of the equivalence class of X and Y is the equivalence class XY, where again the XY inside is the product of integers, which we already assume makes sense. And or if we write this in the coset notation, and notice I just did something a little bit, you might have missed it. This notation right here, we say Z, mod NZ, that is Zn, okay? There's another notation for that. This is actually the set of all equivalence classes, modulo n, all right? So it's the set of cosets, in other words. All right? And so here's what the definition of modular arithmetic looks like in the coset notation. X plus nz plus y plus nz is x plus y plus nz. And over here, x plus nz times y plus nz is xy plus nz. So, you know, in some sense, if you want to just kind of think about this formally, when we have nz plus nz, we just get nz back again. Whenever you have like a multiple of nz, you can just, if you have a couple of them, you can just keep one. It's kind of a heuristic way to remember this. But in other words, and more plainly, you just add the representatives or multiply the representatives. That's the product and sum. Okay. And like I said, we use this notation often. Z mod n is what's this called. Often we verbalize this Z mod n. It's the set of cosets, the set of equivalence classes, modulo n. All right? And the beautiful thing is that, you know, okay, so this definition only makes sense because we've already proved that this sum does not depend on the representative chosen, right? I mean, otherwise there'd be a big fat question mark here. Why would this make sense? Because I told you before that, you know, x equal to x prime equivalence classes does not imply x and x prime are the same thing, right? So, and for this to be a binary operation, we would need that x plus y and x plus y prime, the equivalence classes for x plus y and the equivalence class for x prime plus y prime would have to be the same, right? And if they were different, then that wouldn't be single valued. It wouldn't be a binary operation, but it is because we just proved that. You know, that this proposition we just went over implies that the definition of modular arithmetic is what's called well-defined. All right. All right. More than that, it's got awesome properties. Well, I mean, I don't know if awesome is the right word, but nice properties. Addition's commutative, multiplication's commutative. You got this handy-dandy distributive property both ways. You have associativity of addition, associativity of multiplication. The equivalence class of 0 behaves like the 0 for the set, right? And the equivalence class of 1 behaves like the multiplicative identity, just like that, all right? I didn't actually prove any of those in here, and I assume that might be because I gave you a homework problem on it. So I haven't looked at the homework for a little bit, so I'm doing something risky. I'm going to pick one of these and prove it. There's a chance I'm doing your homework right now. I really don't remember. Let's see here. Which one should I choose? I'm feeling like I'm going to prove this one. All right, so here we go. A, B, right, is by definition AB, right? That's definition of product in Zn, right? And then that is equal to BA because multiplication in Z is commutative. And then of course that is B times A because I'm again using the definition of the product in Zn. Goodness, if I assign this as homework, I feel embarrassed. I mean, this is too easy. Goodness gracious. But anyway, all of these are proved by kind of similar arguments. Here, let me do one more just to pass the time here. How about the one? No, I can't. I mean, I think you guys can work those out. So anyway, those are properties of Zn, and there are even more exciting properties. For example, if you have a sum of, you can extend the sum to like k tuples. I mean, well, sums of k things, I should say. There's k summands here, just like that. And likewise, the product, if you have more, it also extends for larger products. Fine. And of course, this implies that the equivalence class of a raised to the k power is the equivalence class of a to the k. It's kind of nice. And then here's some sample calculations to help you to start see why modular arithmetic is pretty neat. especially for analyzing questions about divisibility and so forth and remainders. It can be very simplifying. Okay, so 1, 2, 3, 4, rather 1,234 to be clear, is 1 times 1,000 plus 2 times 100 plus 3 times 10 plus 4, right? And if we want to simplify this modulo 5, well, you start to look at 10. Well, 10 is 2 times 5, right? So anything that's got a 10, either first or second or third power, necessarily has a copy of 5, right? And so that means that as far as modular arithmetic is concerned, this stuff is all 0, and you're just left with 4. So, so in other words, the equivalence class of 1,234 is just 4. And in fact, you can see that if you had a larger decimal representation of some number, then only the ones digit actually matters, because everything else is going to be congruent to 0 once you expand it out in the base 10 representation. All right, so I think you guys can. Fine. I'll take a minute. Sorry if this is boring. You can fast forward or whatever. Calculate the cube of 51 modulo 7. All right. So, I mean, great. You're like, well, I could do that in my calculator, like using the ideas that we talked about before. That's true, but what if it was, you know, I don't know, a bigger, I mean, there's ways to make this so you can't do it on the calculator, all right? Don't make me do that. Anyway, 51 is what? Well, first of all, 51 cubed is that times that times that, right? But, which is that? Okay, fine. 51 is also 49 plus 2, but 49 is a multiple of 7, which means it's 0 modulo 7. So this is congruent to that, and then, well, that's easy enough to calculate. That's 8. So there you have it. And then here's the same calculation, but with congruence notation. Like, well, which one do you want to use? Which one do you want us to use? I understand both. I mean, I don't know. Depends on the question. Let's see here. Simplify 7 to the 100 modulo 6. All right, so 7 to the 100. Well, this is very silly because 7 mod 6 is just 1. So this is really just 1 to the 100. All right, great. Now here's the incorrect way to do it. I mean, 7 to the 100 is 7 to the congruence class of 100. See, this step right here is bogus. That is not a step that's allowed. And as you can see, it produces a contradictory result, which would be worrisome because, you know, usually we do math, we get one answer, not two, in this sense. So anyway, long story short, these many things are true for congruence, but you cannot take the congruence of the power. All right. Okay. Now, just a word of advice. You know, when you're working with Zn, you've got some choices. You can use representatives, the least non-negative residues. I often use 0 through n minus 1. But sometimes it's helpful to use the least absolute value residues, which are like 0, plus or minus 1, plus or minus 2, all the way up to, you know, however many you need to get everything. The details depend on whether n is even or odd. For example, if it's odd, for example, this 5, then you've got, you know, minus 2, minus 1, 0, 1, 2. Whereas if it's even, it's kind of lopsided. You could keep 2 negative 1s and 1 positive 1. Or to be less weird, how about we keep minus 1, and then 0, and then 1, and then 2, right? Let's keep it positive, yeah? All right, sorry, I'm an idiot. Let's go on. All right. So as I was warning you, you know, when we're working in Zn, there's really not much, there's often not harm in dropping the, so sometimes I'll use like a bar over the x to denote the equivalence class represented by x. Sometimes I'll just use x. It just kind of depends. Where you need to be more careful is when you're trying to prove something about equivalence classes. And when you're trying to use the structure of the integers to prove something about equivalence classes, there you really do need a different notation for integers and for the equivalence class like we have up to this point, okay? But in this next example, it just starts to get to be really kind of a drag to use such notation. So here I'm going to say f of x is x squared plus 2x plus 3 for x in... Now I say x in z5, but what I mean here, that's funny. What I'm saying is that x is a equivalence class mod 5, all right? And so I'm actually writing -2, -1, 0. So this, this -2 is really, I'm really meaning that, all right? But I get tired of writing that. And things in a calculation like this, I'll just write -2 instead with the understanding up here, explicit calculation, modulo 5. I mean, I tell the reader somewhere, hey, I'm doing mod 5 calculation, right? You got to write it somewhere. But you don't have to burden yourself with writing 15 billion, I guess not 15 billion, but a couple dozen, right, brackets here. Anyway, so when you do actually do the calculation here, what do you get? 3, 2, 3, 1, 1. And what that shows is that no matter what residue class we plug into this polynomial, we don't get the 0 residue class, right? Here's a couple more calculations. I'm gonna move on here. I'll let you look at those. Talk a little bit more about this example 12.24 because it's kind of more interesting. Prove that the product of a plus 1, and a plus 2 is divisible by 6 for each integer a. In other words, we wish to show that a times a plus 1 times a plus 2 is congruent to 0 mod 6, all right? So what I do is I just plug in the different, we either got 0, plus or minus 1, plus or minus 2, or 3. And so when you plug those in, you get 0. You get 60, which is congruent to 0 mod 6. And then for the plus or minus cases, depending whether you check plus or minus, you either get 6 or 0 or 12 or 0, both of which are congruent to 0. So in every case, this expression works out to 0 mod 6, which shows you indeed the product of three things is in fact divisible by 6 for any integer a. Now if you just start thinking about numbers, that's kind of not that surprising, right? And in fact, if you think about the numerics here, I might think about a different method of proof. So it's the same example, different way of looking at it. This example 12.25. So notice that if 2 divides x and 3 divides x, then that means x is equal to 2j and x is equal to 3k for some j and k. So from the prime factorization of integers, 3 has to divide j, and 2 has to divide k, right? Because you have that 2j is equal to 3k, right? And there's no way that this 3 is dividing the 2, right? So if 3 must be dividing j, then that's a consequence of the prime factorization of integers, which we'll talk more about here in a second. But anyway, so 3 divides j, 2 divides k, therefore there exists m such that j is equal to 3m, and so x is equal to 2j, which is equal to 2 times 3m, which is 6m, which proves 6 divides x. Therefore, we're able to show that if we're able to show that the product of these three things divisible by 2 and 3, it then follows that it's divisible by 6. All right? And so what I do is go through the same argument we went in the previous example, but this time, once for mod 2, I just check 0 and 1, congruent to 0, equal to 0, congruent to 0. And then we check mod 3 for the product of a plus 1, and a plus 2, and again we get, plugging in 0, 1, and 2, the equivalence representatives mod 3, we get 0, 0, 0. So that implies it's divisible by 2. That implies the product a plus 1, a plus 2 is divisible by 3, so by the argument we just went through at the start of the example, it follows that it's divisible by 6. Now, so that's kind of an interesting calculation. I don't know, that kind of surprised me when I first read it. And it goes back to this important fundamental theorem, the fundamental theorem of arithmetic, and I'm not going to prove it. If you'd like to see a proof of it and a much deeper discussion of it, maybe you should take number theory. Maybe you already have. Anyway, so n in the natural numbers, there exists a unique set of distinct primes, p1 through pk, and multiplicities, r1 through rk, such that n is equal to p1 to the r2, p2 to the r2, pk to the rk. All right? And here, of course, we're assuming that the, n is positive. All right, fine. All right. And then here's a consequence of that. N is a natural number. There exists a unique set of primes. Multiplicity, that. All right, great. Okay, so that's just what I just said. All right, furthermore, A is congruent to B mod n. All right, here's the extra thing. A is congruent to B mod n if and only if A is congruent to B mod each prime power. So the only way A and B can be congruent is if they're congruent for each prime power. This was the example 12.1.2.25 was a special case of this. All right. Again, I leave the proof to the number theory course. Our heart is elsewhere here. So, but that is sometimes an important technical tool to know about, that theorem I just mentioned. Another important idea, and this one is much more elementary, really, but profound in its application, is that you can look for integer solutions for a polynomial by looking for solutions for the equivalence classes. See, since once we pick a modulus, right, and we look at the residue classes, that means every integer is in one of those residue classes, right? So if when you plug in the residue class into the polynomial, it comes out to 0, that means that at least it's possible that the polynomial hits 0 somewhere in there. But on the other hand, if well, let's just look at the example. I think it's easier to see with an example. Here it is. So x to the 5th minus x squared plus x minus 3 has no integer roots is the claim. So it turns out if we look at modulo 4, so we plug in 0 into that, we get minus 3. We plug in 1, and this is working modulo 4, okay? Plug in 1, we get 1 minus 1 plus 1 minus 3, which is minus 2, right? Plug in minus 1. We get minus 1 minus 1 minus 1 minus 3, which is minus 6, which is congruent to 2. Plug in 2, we get 32 minus 4 plus 2. Anyway, it's congruent to minus 1. So you look at it. This one, that one, that one, that one. Those are your choices. None of those work out to the equivalence class of 0, mod 4. So that means that there's no way that this polynomial outputs even a multiple of 4, right? It's certainly not 0. And so this is a kind of sneaky way of showing that this polynomial has no integer roots, because when we look at this set of equivalence residue classes, we don't get the 0 class back out, right? And again, the 4z, 4z plus 1, 4z plus 2, 4z plus 3 partitions the integers, so we've covered everything by looking at that. Anyway, you can prove that claim I just made. It can be proved carefully. I don't think I've done that here. I've just showed you an idea. So here's the theorem, actually. F of x, a polynomial with integer coefficients, that's what this notation means. That means that f of x is equal to something like a0 plus a1x plus dot 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 plus a k x to the k, where a0, a1, ak are all elements of the integers. That's what this notation right here means. That means that we're looking at a polynomial with integer coefficients. All right, and suppose n is a natural number. If a is congruent to b mod n, then f of a is congruent to f of b mod n. All right, so that's a theorem, and that one actually not too hard to prove. It's basically just repeated application of the corollary we mentioned before. If I have a is congruent to b mod n, then I plug in evaluated a, get that, and then a to the m is congruent to b to the m, and a is congruent to b, and so forth, and so we get the congruence of that, and that's f of b. So there you go. So, all right. So this paragraph talks about contrapositive. I'll let you read that. I'm not gonna. You can read that. You guys hopefully know what contrapositive is. If you don't, read that paragraph. Think about it a little bit. I should mention that all of this I am stealing, more or less stealing, and probably doing a bad job of stealing it, from Jones and Jones Elementary Number Theory, which is a pretty good book, which I almost used when I taught number theory. Let's see here. All right, so while integers and modular integers, or Zn, are similar, they're also very different. All right, and you can see that especially in terms of equations, right? So we saw a system of equations in Z4 had 4 distinct solutions. In the context of equations over the integers, we're either going to obtain no solution, one solution, or infinitely many, as it happens. And this distinction is largely tied to the fact that some numbers in Zn do not have multiplicative inverses. For example, in Z4, 2 times 2 is 0. And yet, that means that 2 does not have a multiplicative inverse. There's no number x such that 2 times x, or the equivalence class rather of x times 2, equivalence class of 2, is equal to the equivalence class of 1, which by the way serves as the multiplicative identity for the Zn. As you see, I'm getting tired of saying equivalence class, so I'm just going to say that 2 times x cannot be equal to 1 mod n, or in Zn. So these zero divisors are troublesome. They're troublemakers. And on the other hand, you might be interested, we are of course interested, when is it the case that there is a multiplicative inverse for something in Zn, right? So suppose we have a, and a is given, and we're trying to find x such that ax is equal to 1. Well, that means that ax minus 1 is equal to nk for some k, right? That gives us that ax plus nk is equal to 1, right? And, I think we already know what that means. That means that a and x must be, what? Relatively prime, right? Well, that means a and n must be relatively prime as well, which is, of course, more interesting because n and a are given already. So in order for a to have a solution to this, we must have that a and n are relatively prime. So the elements of Zn which have inverses are precisely those which are represented by relatively prime integers to n, right? So if you go back to pre-equal 1, we found that the greatest common divisor of 62 and 626 was 2. And that shows that modulo 626, the number 62 does not have an inverse, and likewise the number 626 does not have 62 doesn't have an inverse mod 626, and 626 does not have an inverse mod 62. So you get both of those things from that. Here's a more interesting one. We also find that the GCD of 11 and 240 was 1. In other words, 11 and 240 are coprime. And we furthermore learned from the Euclidean algorithm this lovely equation right here. Well, now we can see things about Zn from this. In particular, here, let me decorate this a little bit here. I'll write it down here in different notation. So what I'm saying is that minus 109, all right, mod, so I could put a 240 down here. It's the equivalence class with respect to 240. The inverse of that is the equivalence class of 11 mod 240. All right. That's one thing we could see, but we could also look at this in terms of, Z5. So this is a comment about something we learned about Z240 from that, right? But we can also see that the, let's see here, oh, I can't do math. Goodness gracious. Minus 109 inverse mod 5 is equal to 11. 5. Well, I think that's especially silly because this, goodness, alright, so if you add 110 to this, what do you get? You get 1. 1 inverse mod 5 is equal to, what's the, that's, so 1 is its own inverse mod 5. Well, of course 1 is its own inverse mod anything, so this is not particularly exciting a result. I mean, this is a little bit more, I think, exciting, the first one I found. But anyway, if you look at one of these Euclidean algorithm calculations we did before, there's a bunch of different things you can see from one of these things. Here, yeah, invert 5 invert. Try to put them on the same page here. Excuse me. Should have got more coffee to drink here. Again, from the purple underlined equation, you can see that the multiplicative inverse of 5 mod 11, so I could put like little 11s down here if you like. So 5 mod 11, the inverse of that in Z11 is 240 in 11, right? Now this could be simplified a lot, right? Because 220 is what? 220 is, I'm trying to think of multiples of 11. 10 times 11 is 110. 20 times 11 is 220. So this is equal to 20. 11, which is equal to what? 9 mod 11. So this is saying 9 times 5. What's 9 times 5? 9 times 5 mod 11 is 45 mod 11, which is 44 plus 1, right? Which is 1. So there you go. That shows you that 9 is the multiplicative inverse of 5 mod 11, right, in Z11. Of course, on the other hand, you could look at the purple underlined equation as a tale about mod 109. So like 5 mod 109 inverse is equal to 11, right? Oh, I'm sorry, not 11. I can't do math. I keep losing track. Oh, 240. 240. I'm sorry, I'm taking too long here. 240, 109, mod 109. And of course, you could simplify that down a bit. Oh, yeah, here we are. So anyway, I hope this shows you that Zn is a thing we can calculate in. It's simply sets of integers where we can add and multiply by adding and multiplying the representatives for the equivalence classes. But from this point on, we are going to use this notation, and I will just say things like 2 or 3 in Zn. I will not say equivalence class most of the time because, of course, it's a pain, and it doesn't really add much to the discussion for the most part, until you get confused. I mean, if the question boils down to a confusion about thinking of these things as integers and as equivalence classes, confusing the two, then we have to get back into this more nuanced notation. But otherwise, let's agree that Zn we will typically denote by either its either these sorts of what's the word, positive, non-negative residues, or by its least absolute value residues, depending on which is more productive to the conversation. Anyway, that concludes prequel 2, and prequel 3 will be about something probably less familiar. So thanks, guys.